Good morning and hello everyone. Today I'll be speaking about some of the dangers and risks that are associated with using off-the-shelf modern day NLP systems and things that you should be aware of that are often goes unnoticeable when using these models because they're so good at writing coherent sentences and things like that. So let's start. Um, I'll be going over 10 things today. Three of them would be going over some of the basic NLP modeling risks, things that you every day use in your workflow, but might not be aware of, or things that I at least noticed tend to get ignored, but end up leading to large errors further down into the machine learning cycle. We'll be discussing 3 ways to reduce biases, and we'll quickly go over 4 tools that you can use to improve your modeling workflow. So in total, 10 takeaways from this talk today, and hopefully this will be a good experience, and I get to share. I'm glad I'm getting to share this all with you. Um, so let's answer the why first. Why is it that we are actually talking about NLP in healthcare? Why is this NLP Summit specifically different from NLP in general? So the first and foremost, in healthcare, transparency is a priority. Regulations exist, compliance exists. You need to explain your decision making to doctors, nurses, people who have spent years just uh, perfecting and learning the craft or skill that your models probably spend a couple of days just learning from the text itself. And that's something that's critical. And if you want to put your models out there in the wild in front of doctors, you need this ability. The second thing is the cost of type 1 errors. False positives can be huge. You can do an incorrect diagnosis or maybe lead a doctor to do an incorrect diagnosis. There can be denial of care for a certain set of individuals and things like that. The third aspect is clinical language is a lot more factual, a lot more nouns, a lot more numerics. So all in all, when you work a lot with it, you realize that it's really different from the way English is being written. The way ideas are being expressed across in clinical setting is different than English. And one other reason for that is because language almost always in clinical notes is being written by a subject matter expert. So your progress notes, it's been written by your doctor, your lab results come from a pathologist and things like that. So which is not the case when it comes to your usual English, where you have different people writing, expressing themselves in different ways, and they might not be experts in one field or the other. But that's not the case here. Then finally, vocabulary is a lot more large as well as diverse when it comes to clinical terminology, and that leads to some assumptions being invalidated when applying your usual academic techniques to clinical terminology. So we'll go more into that further down into talk. Last thing is your usual tendency to work with machine learning is to take this big data set, pass it, pre-process, pass it through ML model, and done. But in NLP, you have these cohorts within your big data set itself that can be grouped or identified by a certain set of characteristics. So for example, you have patients with type 2 diabetes that are given 100 units of insulin 2 times a day. That's very different from patients who are given 100 units of insulin 3 times a day. So all of a sudden, this risk increases. All of a sudden, your ordinality of the numbers present matters. Now, you just simply cannot normalize 1, 2, or 5 or any number to a number tag and call it a day. So that's something that you need to account for. So let's start with the 3 modeling risks. So clinical language is a lot more factual, and to extract these facts in industry-wide technique called named entity recognition is used. This is a technique that's basically used to find entities in a text, organization, location, things like that. Uh, So for example, you see a text, this whole a text here, it has highlights of different types of entities. There's person here, there's GPE, which is or locations and organizations and things like that. Then there's dates in there. However, once you spend some time looking at it, you start to notice where it actually went wrong. So the first thing you notice is where it missed out. So there's a FBI agent outlined with red top right corner that it missed out on. On the left, the New York Times by Adam Goldman is marked as an organization, even though it has a name of a person in it. Bottom right, it's saying Mr. Trump's victory traces back to June. So Mr. Trump's here is marked as organization, which is again wrong. And then lastly, the biggest one here is Michael S. Smith has an og keyword after it as a suffix, and this leads to a cascading error. So og, now this Michael S. Smith is marked as person, while in reality, right after Smith ends, og 13/2018 is actually a date that should have been marked, but instead now 13 is marked as cardinal, 2018 is marked, 2018 Washington is again marked at cardinal, while it should have been two different entities where Washington should have been GP. So these things brings us to our first point, that named entity recognition systems are not 100% accurate. You might have 50 entities in your text. Each of them have an associated error rate in them. It might be 60, 90, 100% correct. Imagine passing all of that down to features as for your classification model, for your custom model, and that will lead to cascading errors, and even worse case, where your model might improve performance, but then it ends up learning the wrong set of patterns from your data set, which you don't want. So you need to be aware of this part. The fix here is you need to pay attention to precision recall of these models, and if possible, test them extensively on your data set that's closely aligned to the task you're doing. So you're taking BERT, but then you have your own evaluation sets, rigorous evaluation sets that you evaluate this on. The second aspect is languages written by experts. So in these notes, which are really lengthy, you often want to extract the rare words, the key words from this for summarization, for modeling, to find those rare diagnosis systems and symptoms and things like that. And that's where a technique called TF-IDF is used. It's a very general technique. Most of the NLP baselines before 2015 were using these. And what it basically does is it's used to unearth rare words in a document. And in that it assumes that common words like articles, determiners, and things like that are less used, are used a lot more than your rare words, for example, adenocarcinoma and things like that. However, in medical terminology, these specific words might end up being used equally all throughout your text, and that basic aspect invalidates the TF-IDF assumption. Actually, it might even backfire on us, where some of the rare words are mentioned repeatedly in your text, but common words are not mentioned easily. So for example, the name Alice might be mentioned at the first level of your note, but then not mentioned anywhere else in a 50-page doctor note. But the name dialysis might be mentioned a lot of times. So you see how it backfired, where dialysis will be given a lot less weight than Alice, because Alice is a lot more rarer compared to dialysis. So this is something that you need to take account for. And the fix would be to basically, instead of just blindly applying TF-IDF, passing it to a estimator, you actually do TF-IDF, you see what it's finding, you actually see what kind of words is it choosing over others. And if it fails, you reduce your vocabulary size, try again, and ultimately you can still revert back to a binary bag of words as feature model, which means you are just modeling on the presence or absence of a certain kind of keyword in your text, and then you can let your estimator decide what matters and what doesn't matter. So that's a much robust baseline, and would not lead you to into big errors further down in your life cycle. The last is vocabulary. Hopefully by this time you might be refreshed with all the pre-processing techniques in NLP. So let's talk about vocabulary. It's it's diverse. It can have Latin names, conditions, dosages, drug names. And in that, the way in you use the term vocabulary, the concept of vocabulary computationally is you basically end up picking the top n keywords that are most frequent in your corpus. So let's say you have a large corpus, 100 million word corpus, and there are unique 1 million words in it. To reduce noise, you end up picking just the top 30,000, top 50,000 words. And you say that, okay, these are the only words that actually matter, and I'm going to use TF-IDF to solidify that and use that as features. Well, why is that a problem in clinical setting? Imagine that the word adenocarcinoma is mentioned rarely in your corpus, but for a patient, that matters a lot. Having diagnosed with cancer matters a lot compared to any other article or any other thing mentioned in your text. So in that case, you don't really want to weed out all the clinical terms just because they are not mentioned or rarely mentioned in the text. You want to keep them around. But then to keep them around, it's a computational cost that you're taking on. You have to keep 2 million, 5 million words in your memory. And when it comes to deep learning, that large number of words becomes the size of your embedding matrix. And that embedding matrix is the first layer of most of your modern day NLP architectures. Now, embedding matrix discharge won't fit into GPU memory, will be a lot harder to train because it will need a lot of much more bigger data sets to train with, no free lunch problem. So the authors of BERT and GPT came up with a really clever hack called byte pair encoding. But let's quickly take a detour and just want to refresh everyone what GPT, BERT, and these things are. These are basically large-scale neural network-based language models that have been found to do very well on a large scale of NLP tasks. NLP benchmarks that were created by academia to test how a given model is performing. There were signs that larger the language model, the better the benchmark metrics. So everyone went in for larger models, large data. And on top of that, training large-scale RNNs became a bottleneck. So people wanted to shift towards other means that could be parallelized. So a lot of innovations went into it, but one critical aspect was the pre-processing. This is what's differentiating these modern day techniques from older ones. Usually, a lot of pre-processing used to happen, but then now the only pre-processing that needs to happen is how your document gets split up into individual tokens. So that's what byte pair encoding is. That's what GPT, your Roberta, your OpenAI's GPT-3 or BERT and all these models have been using. What this does is basically it ends up splitting your whole word into smaller words and then use that to represent your whole corpus. For example, diabetic being split into dia, B, and tech. And then the same dia would be used to also represent dialogue. BERT uses just around 30,000 of words to represent your whole English vocabulary, which is great because it reduces the size of your embedding matrix, and now you can train much larger models. So it works, and definitely since the models are so large, they're able to model this part. However, when it comes to clinical setting, you have 1,000-word long document, and on average, your clinical terms, Latin words are a lot larger. Your byte pair encoding ends up splitting these larger words into a lot of different smaller chunk subwords, which really doesn't make sense. And in the end, it ends up increasing the length of your document 3 to 5 times. So now your 1,000-word document is 5,000 words long. And that in of itself is a modeling problem because you need to now bring in techniques that model longer range dependencies, which is again a bigger problem in of itself. So the question is that how we read language? Before BERT, that wasn't the case. We were using actual words to represent something, but now these smaller subwords are being used. So you need to keep this in mind. There's no fix for it. If you change vocabulary, you have to completely retrain from scratch. So you keep this in mind when you're doing fine tuning and things like that. Observe how your tokenizer is splitting your actual clinical terms. So these were the three modeling risks that I wanted to go over. Now let's look at some ways to reduce the biases that are present in these models itself. So as I mentioned, there are subgroups in this large corpus. Your model in of itself is a compression of the data set that you train it on. Your GPT-2's training data set was from Reddit. It's a forum where an independent research found out that 60%, 7% of it was being posted by men, and most of them were between ages 18 and 29. Now, GPT-3 was trained on an even bigger version of this data set. Imagine what happens when you take the text written on it, the language models that were built out of this, and use it to fine tune on for clinical text. Even if you forget this aspect, you can still use things like CyBERT, BioBERT, and things like that. But at the end of the day, those are still using the byte pair encoding tokenizer that I mentioned in the beginning. So we have to be really careful on what our models are trained upon. So one quick side effect of this would be, since the data sets are so imbalanced, they could end up inheriting biases. And there are a couple of papers, some of them I'll just quickly show you. One of these papers found out that not only does the data set have biases, but the models end up actually amplifying this bias at test time itself, even up to 70%. Another thing is another paper found out that there is definitely significant gender bias in BERT. The completely different linguistic aspect is these models end up exploiting like the statistical cues in the data set itself. They don't learn anything about the underlying grammar, underlying structure of the sentence itself. Instead, they just exploit syntactical cues that are present, for example, lexical overlap, subsequence heuristic, constituent heuristic, and things like that. Well, there are methods to fix it, but if you're just using off-the-shelf NLP, you have to remember that it might just be cheating its way out for getting you to a prediction. Okay, so the three ways you can easily reduce biases is normalize PHI if you're working with it, normalize names, organization names, dates, things like that. The other way is to identify cohort agnostic and cohort dependent features, which means that some features are commonly prevailing across all your data cohorts, but then there are some that are dependent, which means age is a factor. Kids only diseases, symptoms limited to females, and things like that. So this risk stratification needs to happen by the data scientist who is actually working on the problem and needs to spend time on it to find out what these subgroups are. Once these are identified, now you can write samplers that sample these cohorts, data from each of these cohorts equally during model training, so that model doesn't end up cheating its way out of it. The other thing you can do is, if you have the luxury of a lot of data, you can actually split up into different cohorts and then train individual model on each of them. And then finally, if once your model is trained, do some analysis, find out whether the FPR of your model is same across these cohorts. And if not, you can use simple ways to adjust FPR so that your performance is equal across all these cohorts. So those are your three ways you can reduce bias. But up until this point, there were so many drawbacks and there are so many biases. Does that mean you need to just go back to logistic regression? Well, by knowing risk, you can mitigate them. If your application isn't really susceptible to these risks, you can go ahead straight up use them. But at least you know now that these are the risks that actually are inherent in these models. So Maybe you can reframe the problem and build risk-averse application, which means you are not denying anything to it. You are letting the humans deny, and you're actually using ML to just approve the easier parts. You can also, instead of trying the problem at large in just one zero or one situation, you can actually find clues and offer it to humans and say that, hey, these are the things that I found in the text. This is my confidence, and now it's up to you whether to use it or not. And that will be a much better proposition than just saying that, okay, I found this to be a chronic disease, acute disease, or things like that. Devil really is in the details this time here. Byte pair encoding, length of the document matters because the original authors trained on documents that were only 128, maximum 128 words long. So now if your documents are longer, there's slight overfitting and dependence on this length. So those are some things. And then, of course, biases is in of itself a thing. So build solid baselines. Don't directly jump to using BERT, GPT. Logistic regression can be a good baseline. You can use BERT to tell you what are the inefficiencies in your data set, and then maybe you can just find those inefficiencies, fix those, and build even simpler models out of those. So it can be a guider for you to build better models. And then finally, equip yourself with better diagnostic tools. I'm going to skip on this one, but basically, as an alternative, there are methods out there that have equivalent performance as transformer, but use a much simpler LSTM-based models and do not need any hyperparameter tuning and things like that. With a lot more less compute power dataset, these methods are equally performant as BERT, GPT, and things like that. So you need to do your due diligence. You need to try different things and not just take things for as they are, as in BERT. Let me just go ahead and use it in myself. I have found in my experience to have simple CNN, RNN models perform way better than BERT. So definitely try bet things out, build solid baselines. Now, with all these advanced models, which are already giving you pre-trained models out there, your job automatically has shifted from being just training models. And now actually, once your models are trained quickly with this pre-trained models, your job starts there once your model training ends. So now the debugging needs to happen. Now the quality assurance needs to happen. So let's discuss 4 tools that will actually improve your modeling and help you find like problems in your data sets or models. So for the first one is this, the author, I think Marco already gave a talk last year, but this is an excellent paper. They gave out a checklist that you can use to behaviorally test your NLP models. In this case, this is for general English, but you can take this and work with your QA team or yourself, and you can basically end up creating a nice set of unit tests, NLP unit tests that can always run on your black box models, and that will help you a lot in finding out the inefficiencies in the model itself. The second thing is language interpretability tool, great tool by the Pair Lab from Google, and it has everything one could ask for when trying to diagnose your models. What are the false positives and things like that. The third one is concept activation vector. So I just wanted to spend a little more time on it. What happens with TCAP, what you can do is, if your doctor says that, okay, I need to verify whether this NLP model is actually leveraging diabetes, presence of diabetes in ancestors or family history, presence of diabetes as a feature for predicting, and is that something that this model is using or not? So what you can do is you can ask the doctor to label a certain set of documents with the span of exactly where this feature exists, and then you can use those set of documents along with this TCAP technique to find out whether your primary mother base model is actually using this as feature or not. And this is a very efficient technique because now you can actually work with subject matter experts, ask them what is it that actually matters, and you can quickly come back and verify whether this large scale model is using these facts or not. So this has been found to work well in practice. This is again from Pear Lab. And the last thing is, it's not related to NLP, but it's related to the machine learning in of itself. Even once you have this NLP, BERT, GPT models and their internal representations, you essentially are just training an extra layer on top of logistic regression and trying to classify things. So that's where the machine learning aspect actually comes in. So now you need to see that, okay, within these sub cohorts, how is my model performing? And that's where this what if tool plays a really nice role. So you can use this to see how your model is performing across different strats of your data set. And from there on, you can identify, okay, if there's this cluster that's always getting identifies as false, you can then take measures, train auxiliary models to specifically target that. So that's these three tools, all of them from Pear Lab, are amazing and has helped a lot in identifying crucial problems with our models. And even your simpler models, it doesn't have to be BERT, GPT, or things like that. Even if you're training any black box models or even logistic regression baseline, you can always invest energy and time into getting a solid checklist out there that can always be run on your models. And basically this can be your final QA step before you put things in production. This can be part of your debugging pipeline. You can make the things as much automated as you want. So finally, I just want to say that with all of this, NLP is a vast field. Before the past decade, it usually sat in as lab semester projects, but now it's actually having real world implications. And although there are a lot of best practices out there, it's still an open field, vast field. And doing this in academia is different than in industry, because as I mentioned, in clinical setting, cost of false positives can be large. So you need to take that into account and bring the discipline of engineering back into NLP. So having extensive quality assurance pipelines, extensive unit tests for your code base, having good code coverage, good test coverage, and using solid separation of concerns, object-oriented programming, and things like that will really help you in the long run in building a robust NLP pipeline. And then the other aspect is, once you bring this discipline of engineering and then you bring the rigor of science, which is you set up good hypothesis tests to validate whether actually a model is helpful or not. You focus on reproducibility, Dockerize, containerize your experiments, have everything checked into Git or versioned, and have good experiment designs. Multivariate test brings in risk if not done properly. So try to change only single variable at a time and measure. Be scientific about it. So let's bring the discipline of engineering and rigor of science back into machine learning. And that's all from my side. Thank you.